Okay, let's pick it up where we were last time. So generally what we're talking about, we talked about modulation, we talked about detection, we figured out how to calculate the probability of error, but this calculation left several parameters. The parameters that we're most interested in are Z, the threshold, and H of K, the detection filter. So last time what we did was we talked about the optimal calculation of the optimal threshold value. We figured out that if the bits are equiprobable, then we pick a point halfway in between the two noise-free filter outputs. Today we're going to talk about the optimal filter design. So we're actually going to complete the design problem. So we'll talk a bit about optimal filter design, and that will also give us some insight on optimal signal design. So we'll go back and start talking about, or finish talking about energy per bit, and show that the best performance in terms of energy per bit comes when you design your signal sets in a certain way. So let's remind ourselves what we were talking about last time with an example. So this would be an example of optimal thresholds. Okay, let's say we have, so let's remind ourselves the expression for the optimal threshold looks like this. Z is equal to sigma squared over S0 minus S1. Log, by the way, this is natural log. Whenever I put log without a base, I just mean natural log. Log probability of 1 divided by probability of 0 plus 1/2 S0 plus S1. Okay, let's first remind ourselves of some of the properties of this expression. So what happens when the two bits are equiprobable? So where does that come in? That comes in here. So the two bits are equiprobable. Probability of 1 and probability of 0 are both equal to what? 1/2. So this expression is 1/2 over 1/2, which is 1. Natural log of 1 is what? 0. So this term wipes out, and we end up with, so if this is the equiprobable threshold, and does anybody remember the physical interpretation of that?
Half.
It's halfway between, that's right. So if we have S1 down here and S0 up here, the idea is we pick the crossover point between these two distributions, and that's exactly halfway between S1 and S0. So at each point, we're picking, so on this side we pick 0, and on this side we pick 1, and at each point we pick the most likely explanation. So this is where exactly halfway in between S1 and S0 is where those two Gaussian densities cross over. So on this side, this is the density assuming 0%, and this is the density assuming 1%. So a 0 is much more likely than a 1. On this side, a 1 is much more likely than a 0. So on this side we pick 1, and on that side we pick 0. So let's think about, suppose the optimal threshold Z is equal to 0.5. And the values of the other parameters, let's say S0 is equal to +1, S1 is equal to -1, sigma squared is equal to 1. And the question is, find, if 0.5 is the optimal threshold, find probability of 1. Okay, so firstly, let's think about this. If S1 is minus 1, and S0 is plus 1. And my optimal threshold is here. Do I expect probability of 1 to be larger or smaller than probability 0? Larger. Why?
Because you're encompassing more of the Gaussian.
Exactly. So this threshold boundary is encroaching on sort of S0's territory. So basically, it's gobbling up more because S1 should be more likely. In other words, we're biased towards choosing S1 rather than S0. So let's see if that turns out to be true in practice when we calculate it out. Okay. Problem is find probability of 1. Here's my expression. Let me write the parameters at the top. So Z is 1/2, S0 is plus 1, S1 is minus 1, sigma squared is 1, and the problem is find probability of 1. Okay, so basically what we got to do is we got to solve this expression for probability of 1. So let's start by Z minus 1/2 S0 plus S1 is equal to sigma squared over S0 minus S1 log probability 1 divided by probability 0. Okay, so I can take this over. Z minus 1/2 S0 plus S1 times S0 minus S1 divided by sigma squared is equal to log probability 1 divided by probability 0. Okay, at this point, let's substitute in some of these quantities. So we have Z is equal to 1/2. So we have 1/2 times 1/2 minus 1/2 times S0 plus S1. What's S0 plus S1? 0. It's 0. So 1/2 minus 0 times S0 minus S1. What's S0 minus S1? S0 is plus 1. S1 is minus 1. So that is
S squared minus
pardon me?
S squared minus S squared.
So this is 2 divided by sigma squared, which is 1. So on the left, I have 1. So 1 is equal to log probability 1 divided by probability 0. I'm going to take e to the power of both sides. So e to the 1 is equal to probability 1 divided by probability 0. What's e to the 1? Does anybody know what e is off the top of their heads?
So it should be less than 1.
Yeah, 2.71 something. Let's just call it 2.7. It's pretty close. Okay, 2.7 is equal to that. Okay, I want to solve for probability 1. So this is telling me that probability 1 is 2.7 times larger than probability 0. So does that jive with my intuition over here? Yes. So probability 0 must be smaller than probability 1. But how do I get the exact value of probability 1 over here?